Good morning. I'm Chris Carberry, CEO of Explore Mars, and welcome to the fourth and final day of the Humans to Mars Summit. We hope you've enjoyed the previous 3 days. We've had a spectacular lineup of speakers, and we will continue to have a spectacular programming today as well, which Janet Ivey, our president, will tell you about in a moment. But before I turn it over to Janet, I want to thank our sponsors once again, including Aerojet Rocketdyne, Lockheed Martin, Boeing, Northrop Grumman, ULA, the United Launch Alliance, Qualtech, the American Astronautical Society, Paragon, and MDA. Thank you very much to our premier sponsors for supporting this event. We could not have done this without you. I also want to remind everybody, hopefully when the world is at least back to some semblance of normal in May of 2021. Time is so confusing these days, I can't even remember if it's forward or backwards. But in May of 2021, May 11th through 13th, we'll be doing the live, in-person, we hope, Humans to Mars Summit at the National Academy of Sciences in Washington, D.C. again. So we hope you'll be able to join us there. We hope we will be opening registration in sometime this fall, probably in October, but don't hold me to that. It'll be sometime in that time range, but stay tuned. We hope you'll be able to join us again next year for the Humans to Mars Summit. But without any further ado, I want to hand it off to Janet.
Hold on a second, guys. Yeah, so the stream key isn't working. They're sending me a new one right now. We're live, but we're not live, so we're gonna have to start over in just a moment. So we'll probably start like right at 8. Give me just a second. They're sending me new stream keys.
So how are you sending this to?
I'll let you know in the message that we've tried to go live again. 1 second.
Oh, okay, so we just stay put.
Yep.
Okay.
It wouldn't be 2020. So you see that countdown live?
I don't see it. No. Oh, no.
And go.
Yes. Good morning. I'm Chris Carberry, CEO of Explore Mars. Welcome to the fourth and final day of the Humans to Mars Summit. We hope you've enjoyed the previous 3 days. We've had some wonderful speakers, programming topics, as well as a lot of students that have spoken as well to tell us how they've been inspired by space exploration and the dream of going to Mars and why they persevere in these hard times because of that dream of going to Mars. And before I introduce our president, Janet Ivey, in a few seconds, I want to thank our sponsors once again: Aerojet Rocketdyne, Lockheed Martin, Boeing, Northrop Grumman, United Launch Alliance, Qualtech, the American Astronautical Society, Paragon, and MDA, which are our premier sponsors. So thank you very much for supporting us. Without your help, we could not have run this conference. And before I hand it off to Janet, I also want to remind you that hopefully we'll be live again next year. Hopefully we'll have a semblance of normalcy again. And we plan to be back at the National Academy of Sciences in Washington, D.C. on May 11th through 13th, 2021. And so we hope to open up the registration for that this fall. So stay tuned. It should be a wonderful event. And hopefully we'll be able to see each other face to face once again. But without further ado, I want to hand it off to the president of Explore Mars, Janet Ivey.
Thank you. And mainly, guys, I want to also just tell you thank you for being here with us. As our technical director, Wade Holler, said this morning, we're welcome to the biggest and best online live space conference there is. So we know we've had, again, in this new landscape, there are also always some bandwidth issues and things like that, but your staying power is not lost on us. I also want to give a shout out this morning to my predecessor, Artemis Westenberg, who is now President Emerita of Explore Mars. She has just been delightful and has guided me quite a bit through this year as president of Explore Mars. It's been an extreme honor and pleasure to work alongside Chris Carberry, Wade Holler, Ron Sparkman, and the entire board of directors, our board of advisors. All of those areas are growing by leaps and bounds. But just a shout out to Artemis Westenberg, who, again, I believe in that kind of like a slogan of strong women empower other strong women. So a big thank you to Artemis this morning. And that is going to lead me straight into telling you about our programming for today. So we have up first, you're going to hear from Dr. Tanya Harrison. Then we have the wonderful Martian, probably my favorite Martian, Dr. Jim Garvin. Then we're going to talk about planetary protection with Lisa Pratt, Alan Stern, and Mike Gold. In the afternoon, you'll see us talk about how we're going to utilize the ISS to advance human exploration to Mars. Ron Sparkman has an amazing interview coming up with Bo Back-Ferdowski. That is at 1 p.m. Vera Miliani, who of course heads up Mars Cities and Space Design, is coming up at 1:30. You're going to hear from more kids. We'll talk about maintaining political momentum for space exploration. And we're going to end the day with a panel we're calling Why Persevere. So we will be asking you guys to maybe tweet that out, hashtag Why Persevere, because Mars awaits. So without further ado, I would like to introduce to you our first speaker of the day, Dr. Tanya Harrison. Just an inspiration to all. If you do not yet know her, I just want to give a few things about her, all of her accomplishments. She's a planetary scientist and manager of science programs at Planet Labs, and they are working in the federal arm with science agencies to increase research use of Planet Labs Earth observing satellite data. She previously was the director of research at Arizona State University Space Technology and Science Initiative. She was also on the science team of the Mars Opportunity and Curiosity rovers. And if that weren't enough, she has her bachelor's degree in astronomy and physics from the University of Washington, a master's in earth and environmental sciences at Wesleyan University, and her PhD, Global Scale Studies of Martian Mid-Latitude Landforms, I just like saying that, from the University of Western Ontario Center for Planetary Science and Space Exploration. Her research is in Martian geomorphology. See, I don't even know if I said that correctly. Terrestrial analogs and spectroscopy and glaciology. She is also the author of a book called For All Humankind, The Untold Stories of How the Moon Landing Inspired the World. Please go to Amazon and order it. And now please make welcome my friend, Dr. Tanya Harrison. Good morning, and thank you for being here.
Thanks so much for having me. You definitely made it sound like I haven't slept in the last 15 years or so of my life. So today we're going to be talking a little bit about, sorry, go ahead.
No, I said, I don't think you have based on your CV. And I didn't even read all that is there. That is the thing, right? So I didn't even tell you all about her. If you don't know her, follow her. She's just a leading, it's like, not only is she a planetary scientist, I want to tell you something. Every planetary scientist I've ever met has the best heart. There's a bit of philosophy and moving humanity forward involved in everything that they do. So not only are you going to get great science, you're going to get a great human. Welcome, and I can't wait to hear your presentation this morning.
Oh, thank you so much. So that's a really good lead into the discussion that we're going to have this morning to sort of kick off the vision of the last day of this conference. We want to talk about why we're interested in Mars and kind of look at where the fascination with Mars came from in the first place and sort of the future, looking at what we might want to do there. So let me try sharing my screen. Looks like that's working. So when you think about Mars or Mars exploration, this is probably one of the first things that comes to mind, aliens. And it's definitely one of the things that has driven the entire Mars exploration program even before it was created at NASA. There were all of these visions in science fiction about, fantastical aliens living on Mars. It created an entire genre, and all of this stemmed from, of all things, a pretty crappy map. Maybe that's not giving it enough credit. For the time, it was probably fantastic. In the mid to late 1800s, an Italian astronomer named Giovanni Schiaparelli looked at Mars incessantly through a pretty small telescope, and over time drew these detailed maps of the light and dark areas on the surface. Now, if you go in your backyard with even just maybe a Costco telescope, and Mars is close enough, you can see a lot of these features for yourself. We know today on Mars, the light areas are the places that are dusty, and the dark areas are the places that are less dusty. And a lot of these names that Schiaparelli gave to different places on Mars are still used today. Now, since this was taken through a telescope, or his drawings were made through a telescope, this is actually flipped. So Mare Australe is the south pole of Mars, and then the area near the bottom is the north. You might recognize names like Sidonia, for example, which we'll revisit a little bit later. But then eventually, an American astronomer named Percival Lowell came along and misinterpreted some of Schiaparelli's maps. Schiaparelli had interpreted some of the dark features on his maps to be canali, which in Italian means channels, but Lowell misinterpreted this into English as canals, which by definition are artificially constructed features like the Panama Canal. And from this, he had created this fantastical view that Mars was inhabited by an intelligent civilization that had built a complex series of canals to transport water from the polar caps toward the more desert regions near the equator. And he thought that the darker areas were areas of vegetation that were being sustained by these canals. So, over time, we sent a series of missions to Mars to look for these things. Granted, the views that Lowell had were not widely accepted among the scientific community because we knew from things like spectroscopic studies of the atmosphere from ground-based telescopes on Earth before we'd sent any missions to Mars that the atmosphere of Mars was extremely dry, and we knew it was probably some kind of hyper-arid desert. So we sent Mariner 4 to Mars in 1964, and we saw a lot of craters. Most of the images look like the one here. This is one of the first images of Mars taken by satellite close-up. We didn't see any canals. We didn't even see any channels. We didn't see anything very interesting at all compared to what we thought Mars might have been from science fiction. And this kind of shattered a lot of dreams. It didn't seem to be the most exciting place. It didn't look all that different from the moon. But we went back again with Mariner 6 and Mariner 7, and we still didn't see much of anything. The actual reports from Mariner 4 even say that it was unlikely that Mars ever had much water to begin with, and it never had any kind of ocean. But then this view was changed entirely with Mariner 9. With Mariner 4, 6, and 7, we just got really unlucky in terms of the trajectory that the spacecrafts took past Mars as they were flying through the solar system. And they happened to not pass over all of the interesting features on the surface. They missed all of the giant outflow channels. They missed Valles Marineris. They missed all of the huge volcanoes. So a lot of the things that we take for granted in our knowledge of Mars today, these three spacecraft just happened to miss by sheer happenstance of the trajectories that they flew past with. But Mariner 9 actually went into orbit of Mars. And so for the first time, we got to map out the entire planet. And this completely changed our view yet again. So this, the large picture here is a place called Nirgau Vallis, which is a channel that looks like it was carved from underground. These look like what we call on Earth groundwater sapping channels. So it kind of undermines the dirt and everything on top of it collapses. The inset in the top is a place on Mars called Warrego Vallis that is a dendritic channel system. And these on Earth are carved by places where there's a lot of precipitation, so rain. So we were seeing all these different views of features on the surface of Mars that were carved by water that we had totally missed before. So this was showing us a completely new picture of Mars relative to the perhaps boring view that we were getting from Mariner 4. So now we knew there was water at some point in the Martian past, and this obviously has a lot of implications for life, because on Earth, anywhere that we find water, we tend to find something that has managed to survive there. So we took the next step with the pair of Viking missions. So we have 2 orbiters and 2 landers that went to Mars in the mid-70s. This is obviously Carl Sagan with a scale model of one of the landers. These guys were pretty big. And the goal of these landers was to give us a lot more information from the ground. But the orbiters themselves revealed even more channels and valley networks across the Martian surface, and evidence for possible ancient shorelines along the edge of the dichotomy boundary, which is the boundary between the low-lying northern plains and the higher elevation southern hemisphere. And we saw things like the face and the pyramids. And of course, this reinvigorated science fiction imagination again, wondering if these were features that were artificially constructed. Obviously not embraced much by the scientific community, but it did spark a lot of interest, and some really bad movies like Mission to Mars, much later than the Viking orbiters were there. But it regained some spark of interest in Mars in the general public, I think. But the Viking landers were specifically designed to look for signs of life. And they landed in 2 completely opposite parts of the planet. So you have Viking 2 on one side, investigating an area in Utopia Planitia, and then Viking 1 was over kind of near where Pathfinder eventually landed in the Crissy Basin. And both were equipped with 3 different experiments to look for signs of life. A GCMS, which is a gas chromatograph mass spectrometer, a gas exchange experiment, and a labeled release experiment. I won't get into all the technical descriptions of how those instruments work, but the short version is the GCMS and the gas exchange instrument on both of these missions failed to find any signs of life in terms of what they were specifically looking for. But the labeled release experiment caused a lot of controversy. Now, this experiment was designed to basically look for signs of metabolism in the Martian regolith. This was going to be done by mixing some stuff with the soil that had radioactive carbon in it. And if they detected a release of carbon in these samples, then the implication or the suggestion from this was that there might have been metabolism from microbial life in the dirt. They had a test sample, a control sample that they had heated up to a level where nothing should have survived, to use that to see what the samples would do when you mixed this nutrient mix with it. And then they had their actual sample of the dirt. And in both cases, for Viking 1 and Viking 2, they detected signs of what could have been interpreted as metabolism. And so this led to the suggestion that maybe there could have been microbial life on Mars causing this. But obviously, that's a huge statement to make. And so all of the non-biological things that could be responsible for this had to be taken into consideration. And it was found out that there are a lot of non-biological sources for the behavior that we could have seen. This was especially reinforced after we sent the Phoenix lander and the Curiosity rover to Mars, which both found perchlorates in the soil. And the particular types of perchlorates that they found could cause the same chemical reactions that were observed with the labeled release experiment. But those experiments have also never been reproduced on Mars before. And so there's a little bit of controversy there, especially among some of the original authors of this paper, really clinging to the idea that the labeled release experiment did show evidence of life. But since in the general scientific community, the idea was that this was not life on Mars, it again had kind of shattered our dreams. So we went to Mars looking for aliens at Canals and maybe intelligent Martians, got there and found nothing, came back with better missions, found signs of water, but then didn't really find conclusive evidence of life. And so it's just been this will there, won't they relationship with Mars in terms of, are we going to find evidence of life or not? And so from this, the idea was to maybe pivot exploration to look for different things. But then we got thrown a literal curveball, or rather a meteorite. In 1984, the Allen Hills meteorite was found during the one of the expeditions for ANSMET, the Antarctic Search for Meteorites. And it wasn't until the mid-90s that this meteorite actually caused a lot of controversy. A team led by David McKay did some analysis of the asteroid meteorite, my apologies, and they found features that they interpreted to be nanofossils formed by bacteria. Now, this definitely caused a lot of controversy in the scientific community. And if you go to the original paper in Science, there are a couple of replies to that original paper. But over time, scientists looked at this and they came up with a lot of arguments against this being biological. The features were extremely small. They resembled some of the artifacts that you might get from the coatings that you put on these samples to look at them through different types of electron microscopes to do these analyses in the first place. And we found mineral structures after this that could have been formed from non-biological processes that we didn't actually know existed before this. So this not only taught us a lot about biology, it taught us a lot about how minerals can behave on Mars and in meteorites and here on Earth. Now, this led to a bunch of announcements early on before the argument sort of came to a rest in the scientific community that this was not life. Bill Clinton gave an official statement saying that perhaps we had found life on Mars, and lots of excitement in political cartoons as well. So we might not have found life on Mars with Allen Hill's meteorite, but it did spur the entire field of astrobiology after that. And so we have a lot to thank for this, little bit of a curveball coming from Mars. So between this and the failed experiments on Viking, the idea was, let's follow the water, because we know there was water on Mars. And so if we can track down what that water was like, where it was, how long it was around, and what happened to it to make Mars turn into the cold desert that it is today, maybe that will tell us something about the history of life on Mars. And we found a lot of water all over the planet. Almost everywhere we look at this point in some way. We've found buried ice from trenches dug by the Phoenix lander. There's obviously ice in the polar regions. We've discovered new ice excavating impact craters that are smashing into the northern plains of Mars and digging up ice that's buried just maybe even centimeters below the surface. There are water ice clouds. So these are made up of little water ice crystals. We've found tons of places that have both youthful water flows in maybe these Martian gullies that are on the right here, sustained flow of liquid water in places like Eberswald crater and Jezero crater, where Perseverance will be going, in these places where we have these big delta systems, and recurring slope lineae, which were discovered just in the last decade. And these might be really, really salty, so highly briny flows of water that make it onto the surface in warm times of the year on really warm slopes and then slowly sublimate away. So they go from liquid to vapor. We see frost accumulating around the polar cap as you move from spring into summer, from winter into spring. And then as you move from spring into summer, that goes into the atmosphere and forms a lot of these water ice clouds. We not only saw with the Phoenix lander this buried ice that I mentioned here in these the trenches on the right, but we also saw frost on the surface. We observed frost at some of the Viking landing site photos as well. And we see these polygons all over the surface, which are really common on Earth in the Arctic, forming from freeze-thaw action. So places where you typically have ice that isn't very far from the surface. So this helped reinforce the view that we had from orbit, being able to see polygons like this and frost deposited in the satellite images, that there's actually a lot of ice just below the surface and this little thin coating on the surface every once in a while in the right times of year. This is a close-up view of one of those ice excavating impacts that I mentioned. At this point, there have been dozens of them observed on the planet, and actually the Mars Reconnaissance Orbiter monitors for them in certain regions now. The heartbreaking thing is that one of these ice excavating impacts is not very far from the Viking landing site in Utopia Planitia. So perhaps if we had been able to dig a little bit deeper, or we'd landed in just a slightly different area, we would have made this discovery of buried ice 40 years ago. But that's science for you. These are the cloud systems that I mentioned. So all of the blue areas here are water ice clouds observed by the Mars Color Imager, or MARCI. And you can see there's quite a lot of them. So this image was taken in late springtime, when most of that frost that collects around the polar caps in winter, specifically the northern polar cap, has sublimated back into the atmosphere. And the atmosphere of Mars is so thin that it can't hold all of that, and so it condenses out in the forms of clouds. There's also some puffy pink areas you can see here. Those are actually dust clouds. And if you can see my mouse, this here is actually a huge dust storm moving through Utopia Planitia. So we were finding evidence of water all over the place, or at least a lot of water in the past, not a lot of water today, but at least a lot of frozen bits of water here and there. And that has a lot of implications for the history of Mars and the implications for life. Maybe Mars used to look something like this, where we had these oceans, we had these complex river systems, we had lakes. We see a lot of evidence for all of these things today, but we don't fully understand what happened to turn it into what it is today. We do have observations from things like the MAVEN spacecraft that have confirmed the hypothesis that the Martian atmosphere is being slowly stripped away by the solar wind. And that definitely contributed to the loss of water and clouds and atmospheric pressure and all of those things. But if we take a look at Mars over time and plot the history of Mars with the history of life on Earth, this orange area here, Mars was probably only something like the slide that we saw before this until about 3.7 billion years ago. This is what we would call extensively wet Mars. And by about 3 billion years ago, Mars is probably like the Mars we see today, this cold polar desert where there isn't any liquid water really on the surface, maybe in these brief spurts like the recurring slope lineae, but in general, you don't have lakes, you don't have rivers, there's certainly no ocean. Looking at this, Mars was Earth-like and then completely dried out before eukaryotic life, so things like animals, ever arose on Earth. But there is an overlap here between when life arose on Earth and life arose on Mars. So this raises an interesting question. If you had two planets that are right next to each other, and both of them had the conditions for life to survive and arise in the first place, but you got life on one planet and not the other, why did that happen? That's a really important question for us to answer. So we know from all of the missions that we've sent, the satellites, the rovers, the landers, we know that Mars had a lot of water in the past. We know from a lot of different measurements that we have from all the landed missions that Mars had chemical conditions and all of the conditions in the water, things like acidity and temperature, for life as we know it to thrive. So we know that Mars was habitable at some point, but just because it was habitable doesn't necessarily mean that it was ever inhabited. But if there was never life on Mars, that's still telling us something important about Earth. And so if we keep looking for Martians and we don't find them, that's okay, because it tells us that there was indeed something special about Earth that caused life and this vibrant ecosystem that we have here to arise and made it unlike anything else in the solar system. And this is why we study Mars. It's not necessarily to understand Mars itself. It's to put us in terms of humans and Earth in context of the solar system and the rest of the universe by truly understanding just how unique or maybe non-unique we really are. And with that, if we have any questions from the Q&A, we have a few minutes left.
And we're just awaiting questions to come in right now. Our team is gathering them, and I will let you know here in just one moment. So, Tanya, let's talk a little bit about how, while we wait for this, how you actually got into why Mars. Like, what is it for you in particular that made you love it so much?
It was Mars rovers more than Mars itself. When I saw the Sojourner mission drive out onto the surface of Mars back in 1997, child Tanya was just super excited about that, and I really wanted to work on Mars rovers. And then after learning about the missions and why we were going to Mars in the first place, then I got interested in Mars as a planet, and I really wanted to know what happened to turn it into this desert that we see today, because it's absolutely nothing today like it was early on in its history.
And this is a great one from Top Sweeney. She says, could it be possible that there may be some kind of extraterrestrial life on Mars that doesn't require the same fundamental elements that we need for life to exist on Earth? So, second Genesis, what do you think?
That's a great question. And I don't think we can definitively say yes or no, because we only have one sample set for life in the universe, right? We have Earth. And so everything that we're doing is in the context of life as we know it. And that's why I made that caveat on the last slide. Life as we know it could have survived in the conditions on Mars in the past. That doesn't necessarily negate that there's something that has managed to stick around until today that is some kind of exotic form of life that we just can't comprehend, because we have nothing like that on Earth, and we have no conditions like that on Earth where something would need to have developed to survive. So we haven't found anything yet, but I wouldn't completely rule it out because we've only been looking for a very small amount of time in the grand scheme of the universe. And the ability that we have in terms of what the rovers and the landers can do is still quite limited compared to laboratories we have on Earth and things that geologists and biologists could be doing if they were on the surface of Mars themselves. So I think once we send humans, we're going to get a whole new revelation of our understanding of Mars. So stay tuned.
So you're saying we should put humans on Mars? So humans to Mars. Sounds like a great idea to us.
Absolutely.
Anything in particular about these current missions that are on their way there that you're super excited about? Any of the three as the world goes to Mars?
Well, Perseverance is obviously going to be really exciting because that is going to send samples back at some point in the future. And we have Martian meteorites like Dallin Hill's meteorite, but we don't know where on Mars it came from. So we have no geologic context for that sample. This is going to be the first time that we get samples to come back from Mars and we know where they came from, exactly where they came from. And we have all of the rover data and the orbital data to put the things that we're going to learn from those samples into context in the history of Mars. The HOPE mission is going to give us some really exciting information about parts of the atmosphere that we haven't necessarily specifically studied with previous missions. And they were really clever about this. They actually consulted with the MAVEN science team and said, what is your mission capable of and where are the gaps? We'd like to make sure that our mission can help address those gaps rather than reinventing the wheel and just collecting data that somebody else already has. And China hasn't mentioned too much about what they're going to do with their mission, but I'm excited to see another country try to land on the surface of Mars. And I hope that they're successful because, the more the merrier, I think, when it comes to space exploration.
It would help if I hit the right button there. So, Dr. Harrison, thank you so very much for coming on and joining us today. And but before you bow out, you want to let everybody know where they can find you on social media and all the cool things that you're up to.
Sure. You can find me pretty much anywhere as @Tanya of Mars. I'm mostly on Twitter, but you can find me also on Instagram, Facebook, Medium, if you like to read articles. Just look for Tanya of Mars anywhere and you'll probably find me.
Excellent. Thank you very much. And we're going to go to our next panel, and the one and only Janet Ivey is going to introduce us over there to Dr. Garvin. We'll see you all in just a moment.